Good morning, sir. My name is Meghanath. I'm from ECE Department B section. I'm here to share about my concept video. My topic is about loss of thermal radiation. This slide shows us to this slide shows introduction to thermal radiation. Thermal radiation. There are three types of heat transfer modes: conduction, convection, and radiation. Conduction and conver- convection modes are required molecular interaction to transfer thermal energy. Radiation, the only mode that can transfer heat in a vacuum. Thermal radiation definition. The electromagnetic radiation emitted by a certain body as a function of its temperature is known as thermal radiation. So this picture shows us the thermal example of thermal radiation, the sun and the moon. The motion energy of the particles is converted to electromagnetic energy, which is the energy generated by the thermal motion. Electromagnetic energy is nothing but the radiant energy. Body. Any physical object of interest to us, all bodies emit radiation so long as the object is above absolute zero. This is why we humans will glow in infrared cameras. We are emitting radiation. It is just too weak for our naked eyes to detect the glow. So in this slide, body is nothing but uh, body is nothing but every body emits the radiation. Every body emits the radiation, electromagnetic energy. Way to describe the waves of a body is electromagnetic field which travels through the space. Laws of thermal radiation. There are four laws of thermal radiation. They are Kirchhoff's law, Stephen Boltzmann law, Planck's law, Wind's displacement law. So these four laws explain us the thermal radiation. Kirchhoff's law. In heat transfer, Kirchhoff's law of thermal radiation refers to wavelength, specific radiative emission and absorption by a material body in thermodynamic equilibrium, including radiative exchange equilibrium. This picture shows the example for Kirchhoff's law of radiation. Stephen Boltzmann law. Stephen Boltzmann law statement that total radiant heat power emitted from a surface is proportional to the fourth power of its absolute temperature. Formulated in 1879 by Australian physicist Joseph Stephen as a result of his experimental studies. The same law was derived in 1884 by Australian physicist Ludwig Boltzmann from thermodynamics. So this slide shows us the thermal radiation law of thermal radiation set by the Stephen Boltzmann law. Stephen Boltzmann. And coming to next one, Planck's law. Planck's radiation law, a mathematical relationship formulated in 1900 by German physicist Max Planck to explain the spectral energy distribution of radiation emitted by a body. A hypothetical body that completely absorbs all radiant energy falling upon it reaches some equilibrium. So this slide shows us the Planck's law, which is derived by the Max Planck. Wind's displacement law. It states that the blackbody radiation curve for different temperature will peak of different wavelengths that are inversely proportional to the temperature. The shift of the peak is a directly consequent to the peak of the Planck radiation law, which describes the spectral brightness of blackbody radiation as a function of wavelength at any given temperature. So this slide shows us another law derived by the Wein's displacement law. So these are the four laws of thermal radiation. Of thermal radiation. Thank you, sir, for giving me this opportunity.